Hello everyone, welcome to section 7.3. In this section we are going to cover what is known as the ambiguous case. This is the one case that we haven't covered yet. So for situations where we have an angle, and a side, or angle, side, angle, we already know that this is good for the law of sines. In situations where we saw side, angle, side, or side, 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 this was good for law of cosines. I've said that if you just have three angles and you don't know a measurement of one of the sides, you could keep those angles and just scale the triangle up and down all you want. Without knowing one of the measurements of the sides, then there's nothing to do. Right? There's nothing you can do. You don't know how big the triangle is, whether it's the scaled up version or the scaled down version. They both have the same three angles. Now we're going to talk about the situation where we have a side, side, and an angle. This is what's going to generate the ambiguous case. So you can use either law of sines or law of cosines. I prefer law of sines. It's just my general strategy. But I'll show you an example where you can also use law of cosines to attack it. So I prefer law of sines, but that's just, I guess, me, the way I kind of learned it. Why do it two ways when you can do it one? This is the strategy that we want to talk about in 7.3. Now, when you have a side, and an angle that's kind of exterior to those sides, you're looking at a situation where you have a triangle that looks something like this. Well, let me make this a little more clear here. Yeah, that'll kind of make it a lot clearer. Side, side, angle. Right, so again, sides are touching, but the angle is exterior. It's not an interior angle. That would get us back into this situation. It's an angle that's opposite one of those sides. So when we come into a situation like this, we don't know what these two angles are, but we do know the measurement of this side. Right? It has a specific length, but I don't know that it is this, what I like to call this open triangle, or if that length is going this way, creating this smaller triangle. I don't know that because I don't know this angle is a small angle and a big angle here, or if this is the small angle and this is the big angle, because I don't know either of those angles. And this measurement is exactly the same as this measurement. That's how a compass works. Right? You never see a compass, right? You put the thing in the center, and then you can go from here to here to here to here. Right? The distances are all the same. Same thing, if I go from here to here or here to here, the distances are the same. So this distance and this distance are the same. I'm respecting the measurement of the side they gave me. I'm respecting the measurement of the other side they gave me, and I'm respecting the exterior angle that they gave me. How am I to determine which case it is? Well, I'm not allowed to. I'm not allowed to say it's the big one, not the small one, because all they did was give me three numbers. Right? They just gave me three units to use. So I can't determine unless I have more information. This creates this ambiguity. Hence, we call it the ambiguous case. So for these situations, again, I like to defer to law of sines. I'll show you how to use it with law of cosines. But different situations can happen. We can have no triangle. We could have one specific triangle, and the ambiguous case doesn't make any sense. Or we could be in a situation where we have two triangles. And that's the one that we want to look out for. What if we're able to generate the big triangle and the skinny triangle all with using their same information? So that's the case that we want to cover. So let's look at some examples and see what happens. So again, if you're ever in a situation where the information presented to you is a side, and an exterior angle to those sides, you have to watch out for the ambiguous case. If it's, any of the other cases where you know what to use, law of sines, law of cosines, then you're good, you're done. But this case, always you want to watch out. Does it produce an ambiguous case? You have to check. You have to check for the ambiguous case. So let's say we have triangle ABC, and we want to find the missing parts with little a equal to, say, 2 inches, little b is equal to 6 inches, and we'll say capital, we need a is equal to 30 degrees. So let's do like a little rough sketch here. We'll say this is a, which is 30 degrees, which puts little a across from it at 2 inches. And b, doesn't matter whether you orient your triangle one way or the other. I'm going to put it up here at 6 inches. Already you can see that, okay, this is a pretty bad picture because look how much shorter this side is. All right, so this is a very short side. Well, it's a general picture, so we just need to wrap our head around it for now. So this is a case where we have 2 sides and an exterior angle, but I can find this angle. I called this little b, so I can find the angle big B using law of sines. Right? So this is a side-side angle case. Side-side exterior angle. If we apply the law of sines, again, that's the way that I kind of like to do it. Start off with law of sines by saying sine of 30 degrees over 2, right? That's sine A over A is equal to sine B over B, or I don't know capital B, but I do know little b. Let's see what this gets us. This gets us, if I multiply both sides by 6 to solve for sine of capital B, 6 divided by 2 is 3. So we've got 3 sine of 30 degrees is equal to sine of B. Now something funny is happening here. That's an exact value that we can find. Sine of 30 degrees is exactly 1/2. Which means 3 times 1/2, that's 3/2, is equal to sine of B. So my sine function is equal to 3/2, aka 1.5. Can that happen? What's the range on my sine function? My sine function oscillates between -1 and +1. That's not a thing. Right? Sine of B cannot be 1.5. Sine only oscillates between 1 and -1. It will never get to that value. There is no triangle. Here's the better picture. This side is too short. Right? So what's happening here is you have a triangle, quote unquote, where this side just falls short. And there's a big old gap. So there is no triangle. Right, so this is the first instance where we have this ambiguity. Hey, here's some measurements. Find that triangle. There is no triangle. It's impossible. The sine function cannot take on this value. Right? And if we tried to find b using our calculator, we would do sine inverse of 1.5. Immediately, your calculator is going to say error. Right? Don't write error on your test as the answer. The answer is not error. The answer is there is no triangle. You have to understand, what that sine function is telling you. So this just means with these numbers, this side's not even long enough to give us a triangle. So that is one situation that can happen with this side-side angle case. It can actually produce no triangle. Obviously, that's not the best case because there's nothing to do, right? We just say there's nothing and we move on to something else. So let's see what happens when, maybe there actually is at least something to find. Let's say we want to find the missing parts ABC. With little a is 54 centimeters. Little b is 62 centimeters. And they'll give us capital A is 40 degrees. So again, let's just kind of draw a picture here. A, we'll call that B, and we'll call this angle A 40 degrees. You have an exterior angle. If this is capital A, then lowercase a must be opposite that angle. And again, you know, it's up to you where you want to put B. I'm just going to put B up top just to be consistent, which means our goal is, again, to find capital B, capital C, and lowercase c. Right? Angle B, angle C, and side little c. We'll start with the same process. Like I said, this is a side-side angle case. Again, I like to default to law of sines to solve these. So we'll start with saying sine of A over A, which is sine of 40 degrees over 54, is equal to sine of B over B. So I don't know angle B, but I do know this is 62. So we'll multiply both sides by 62, which cancels that out over there. So we'll say 62 sine of 40 degrees over 54 is sine of B, which in general tells us that if I look at 62 divided by 54 times sine of 40, and then I take sine inverse on both sides, and if I apply, kind of hard to do here, sine inverse to the left and the right hand side, this tells me that B is, and it's going to be a value less than 1, so I'm just going to approximate it to 0. Not sine inverse. Sine of B is, I'm trying to save some space here, approximately 0.7380, which is good. That means that we can actually find what sine of B is. This tells us that B is sine inverse of whatever this value is. So since this is less than 1, I can plug this in my calculator. Yeah, I know I can reduce that, but it is what it is. B, and using the same significant figures that we have here, I'm going to say B is 48 degrees. Now, when I look at this sine inverse of 0.7380, whatever that sine of B is approximately this, this spits out an angle, but I don't know if that angle is going to be in quadrant 1 or quadrant 2, right? And I don't know that because the inverse sine function is defined for quadrants 1 and 4, right? When I look at the inverse sine function, it goes from negative pi over 2 to pi over 2. But it returns what is known as the reference angle, right? So this says, hey, your angle is a positive 48 degrees. But the calculator isn't going to know any better to say, oh, but it's the one in quadrant 2. It doesn't know that. Or, oh, it's the one in quadrant 1. Calculator doesn't know that. It just says you're looking at a positive 48 degrees either in quadrant 1 or in quadrant 2. So we have two situations. I'm looking at an angle that is positive 48 degrees in quadrant 1, which I'm going to call that B. So I'm going to look at A, B, C, and A, B, C. angles ABC and sides ABC. Now, this is fixed, of course, 40 degrees. Little a and little b are fixed, of course, 54 centimeters, 62 centimeters. I'm going to call B 48 degrees. Now, what that tells me is that I can go find C by doing 180 degrees minus 40 degrees minus 48 degrees, which will tell me that capital C is 92 degrees. That's the leftover amount. That's all this C could be, is 92 degrees. Which means now I can go find little c. That's kind of our choice on how we want to do it. We could find little c by doing sine of A over A is equal to sine of C, which I just found was 92 degrees, over little c. And then I can cross multiply and solve for C, which tells me C times sine of 40 degrees is 54 times sine of 92 degrees, which tells me that I can solve for little c by plugging this whole value into my calculator. 54 times sine of 92 degrees divided by sine of 40 degrees. That will tell me that little c is, and we'll just approximate it to 84 centimeters. Again, I did this in my calculator ahead of time just to save from me typing on the screen here. That way this video is not a whole hour and a half or so. So we're good on this situation, but we haven't covered the fact that when we look at the sine inverse and it returns this 48 degrees, we don't know that it's in quadrant 1. It could have been in quadrant 2. All right, so sine of B will take on this value, this positive value in quadrant 1 and in quadrant 2. Sine of B could also take on this value in quadrant 2. So we have to be careful and check for an ambiguous case. Right when I got to here and saw that I got 48 degrees, I now have to check for the ambiguous case. What is 180 degrees minus 48 degrees? Well, that leaves us with 132 degrees. So I could have this triangle so that this is 40 and angle B is actually 132 degrees. Well, that still fits because this has the same length as this. It could be the big triangle or it could be the smaller skinny triangle. And that would give me 40 degrees here, 132 degrees here. Wait a minute. That's 172 degrees. That leaves 8 degrees to create this skinny triangle. So that means that this could be, well, the notation that we use is B prime. Right, so we call this the prime notation to denote the second possible case for this triangle. That means we could have this triangle, or we could be in a situation where, what's given to us cannot change. Little b is still 62 centimeters, little a is still 54 centimeters, right? That fits. Capital A is still 40 degrees, that always was the case. But now we have what's known as B prime, C prime, little c prime. Right? It could be the skinnier triangle where B prime is actually 132 degrees. That's this large angle here, leaving us with 8 degrees to go find capital C prime. We can do 180 degrees minus 40 degrees minus 132 degrees. That leaves us with 8 degrees. That's 172 taken away from 180. So C prime could be 8 degrees. Which leaves us left trying to find little c prime. Which again, we can start using law of sines. We can say back to sine of A, which is 40, over A, which is 54, is equal to sine of, now I'm using C prime, 8 degrees, over little c prime. Again, cross multiplying, so you can see I'm doing the same work, but I'm doing it now for the skinnier version of the triangle. Little c prime is going to be, we'll cross multiply to get 54 sine of 8 degrees, and then I'll have to divide by sine of 40. So just to save a little space, we'll do it in one step, because we already did it in the last triangle. And again, just kind of respecting the significant figures here, we can write down little c prime as 12 centimeters. Right, now, there are two different cases, and I can't tell you it's this one or that one. I'm not allowed to, because this one solves the entire problem given, and so does this one solve the entire problem given. Right, and that's all they say. They don't say it's the bigger, or they don't say it's the smaller. They don't give you the right to pick one. It could be both, so you have to find both. So you can see the ambiguous case has you doing twice the amount of work. But not all the time. You know, sometimes there is no triangle. This is a case where, I didn't write it down there, 12 centimeters. This just so happens to be a case where we have two triangles. That's just the way it worked out. So again, given this side-side angle case, we want to stay on our toes and check the ambiguous case. And the reasoning behind that is right here. Right? Look at what's happening. You're saying that this sine of some angle is positive. Well, that happens in two places. Right? So you've got to check both places. Right? There's no way of determining whether it's in quadrant 1 or quadrant 2 just based on the fact that sine is positive. That's all the information you have. Sine is positive. Well, guess what? Then you've got twice the work because it's positive in two places. So you have to check them both. Lots of color. I like it. I like it. Okay, let's take a look at, so we saw in the first example, no triangle could exist. Right? It was just kind of silly that one side was too short. We just saw a case where there were two triangles that we had to create. Let's show that, yeah, there can be exactly one triangle. So let's say we're given the task of finding the missing parts of triangle ABC. With, they'll give us capital C is 35.4 degrees. So there's our angle. Little a is 205 feet. And little c is 314 feet. So again, now we've got this picture where here's angle C, 35.4. That means little c is over here at 314 feet. And I'm just going to put A, I'll put A over here at 205 feet. So now this is big C instead of big A, but same process, exact same process. I'm going to use law of sines to say that sine of C, which is 35.4, over little c, which is 314, is equal to sine of, this must be capital A because it's opening up to little a. And so I don't know capital A, but I can plug in 205 for little a. So there it is. Sine of C over C is sine of A over A. Sine of C over C, sine of A over A. So let's multiply both sides by 205. Sine 35.4 over 314 is equal to sine of A. Which, if we approximate this, we get this number that is less than 1. It's between -1 and 1, so there could be a possibility for two triangles here. I get 0.3782. So sine of A works. So we're going to have to go find that A is sine inverse of all this stuff, 205 sine of 35.4 over 314. So we'll do sine inverse on both sides to see if we can pick up A, which tells us this angle A, we get 22.2 degrees. Now that means that this sine of this angle is a positive 22.2 degrees. That could be over here in quadrant 1, or it could be over here in quadrant 4. So if we do 180 minus 22.2 degrees, we get 157.8 degrees. Aha, so there's two possibilities. We'll start with red as this one, 22.2 degrees, and fill out our triangle. Capital A, capital B, capital C, little a, little b, little c, where capital C was given. So that's fixed. We can never change that. Even if there's a second case, it can't be different. That's given. That's fixed. It can't change. That's given. 205. Fixed. It can't change. 314. Fixed. It can't change. And we just found that for us, A, we're writing down as 22.2 degrees. So it's a pretty small angle, meaning this is going to have to be the biggest angle, angle B. Well, let's see if we can find B by doing 180 degrees minus the given 35.4 degrees minus the other angle we just found, A, which is 22.2 degrees. Let me chop this off here. Yeah, we'll leave that there. Which gives us B has to be this big angle, 122.4 degrees. All right, and if we add all these up, we should get 180. 8, that's an extra one. Yeah, so it looks like we're good. That gives us 180 degrees for our triangle. Let me mark down B right here, so we can see that we need to go find little b. So for little b, and again, I'm choosing to default to whatever information I have. We'll say sine of C over C. All right, both of that stuff was given to us, so we know it's correct. Is going to be sine of B. Okay, I do have to use this piece of information that I found, 122.4 over little b. So sine of C over C was given. We know this is correct. Sine of B, which we found, over little b. So we'll cross multiply to get B times sine 35.4 degrees. I put my degree symbols there. Not that, we're not already in degree mode in our calculators, right? So B times sine 35.4 is equal to 314 sine of 122.4, where we'll divide by sine of 35.4 degrees to get B must be equal to 314 times sine of 122.4 degrees divided by sine of 35.4 degrees, which again, using just some significant figures, we'll say that B is going to round to 458. Which again looks good because capital B was a big angle, and that's a big side. Big A was the smallest angle, little a is the smallest side, so it makes sense. Now, what about the ambiguous case? We never checked the ambiguous case. Right? So sine spit out a positive value, and that happens in both quadrant 1 and in quadrant 2. So we use this as a reference angle to figure out what A prime could be, what the other angle choice for A was. So this triangle's finished. Get rid of this. I'll leave my little graphic here. So there's A. Now let's see if we can find A prime. Which means we would have to take 157.8 degrees and do 180 degrees. Well, this is how we found, let's backtrack here and say A prime was 180 minus 22.2 degrees, which was 157.8 degrees. So this is how we would have found our other angle. But is that possible? Could I create a triangle so that A prime let's see, A and C are good. A and C are good. Could I create this other triangle so that capital C is fixed at 35.4 degrees, always has been, always will be. Little a is 205, that's fixed. Little c is 314, that's fixed. If I say that A prime is 157.8 degrees, can you see the problem with this? (157.8 degrees plus 35.4 degrees, which is fixed for angle C, is equal to 193.2 degrees. Does that even make sense? I still have to squeeze a third angle in here and keep this to 180 degrees. I've already passed that. I've already gone way past how many degrees I'm allowed to have in my two-dimensional triangle. Right, so I can't use this value A prime. This value, in fact, makes no sense. Oops, that's an M. It makes no sense to say, oh, well, I've got 157.8 degrees in one angle and 35.4 degrees in another angle. B prime would have to be a negative angle, right? Not going to happen. So this is a situation where there is no second case. This is just one triangle. And so we're stuck with one triangle, namely this one. So we don't even care about the other case. It can't happen. Right? We've already surpassed the amount of degrees we're allowed to have in a triangle. So this is it. The answer is just, it has to be this triangle, which is nice because now we know exactly what the triangle is, right? There's no second case that it could possibly be. So we've seen where one triangle happens. We've seen where two triangles may happen. We've also seen where it's just impossible. There is no triangle. Now, every time I do these, again, this is more personal preference. I start by using law of sines. In my eyes, it's just a little easier to use, especially if you don't have a calculator available. But you can also do this by starting off with law of cosines. And law of cosines, since it's in this case, it still might give you the ambiguity, or I should say it will initially give you the ambiguity, but it's just law of cosines takes a little more calculating because the formula is a bit longer. So I have it on the screen there so you can see it. So I just want to go through one example where it has us find the missing parts of triangle ABC with, see, I was smart, I didn't erase it. This will give us little a is 2, little b is 6, and capital A is 30 degrees. Yeah, we'll withhold the units on this one because we just want to see the general strategy here. So rather than doing law of sines, let's try this with law of cosines. So again, I'll draw a general triangle with capital A here at 30 degrees, which puts little a here at 2 and little b here at 6. Now, if you go back and look at the first example we did, this is the exact same thing as the first example. We know that there's no triangle possible. This side is too short. Right, so this is the same thing. But I just want to show you something that you can compare rather than starting off with law of sines, how you would attack this by starting off with law of cosines. All right, so the angle that we have is capital A. That's the important thing, which means we need to use the law of cosines that has the angle A in it. So A squared is B squared plus C squared minus 2BC times cosine of capital A is the only angle we have, so it's the only one of those law of cosines formulas that we can use. Well, let's start filling in the information that we do have. We have little a is 2, so we need to square that on the left-hand side. We have little b is 6, so we need to square that. Plus, we don't have c squared, that's missing. Minus 2 times, we do have b is 6, times, we don't have little c, that's missing, times cosine of 30 degrees. Okay, well, just to simplify this a little bit, this is 4 equals 36 plus c squared minus 12 times c times cosine of 30 is actually a really nice value. Cosine of 30 degrees is root 3 over 2. So I'll plug that in. Now we're just dealing with a bunch of numbers. So we've got 4 equals, I'm going to write the c squared first, then I'll write minus 12 divided by 2 is just 6, root 3 times c plus 36. So I put the 36 on the end because it's a constant. I put the c squared up front, and I put the term that has just c in it in the middle. Aha, this is a quadratic. Be very careful, there's a square term, and then this linear term c. This looks just like a quadratic equation. So the only way we have right now to solve for c is by using the quadratic formula. We can't factor that. So again, this is why I like to default personally to law of sines when I have a side-side angle, I like to default to using law of sines to get the ball rolling. But you can start with law of cosines to get the ball rolling, but that's a much tougher ball to bounce, right? So we go to our quadratic formula. Now, if this is x squared minus something, x plus something, we would say x equals, but we're not dealing with x, we're dealing with c is the unknown here. So c is equal to negative b, so it's negative 6 root 3, plus or minus the square root of b squared, so it's negative 6 root 3 squared, minus 4 times, in this case, a, my leading coefficient is 1, times c is 32, all over 2, in this case, a is just 1. Again, a lot more cumbersome to deal with, but still gives us something. Just to save space and time, when we do work through this, we will get the value that c is equal to 6 root 3 plus or minus the square root of this stuff, which is called the discriminant, will give us negative 20 over 2. Now, this c is a side. This is going to give us some sort of complex number. Which means this side c, the only hope of a solution, is either 6 root 3 plus some imaginary stuff, or 6 plus 3 minus some imaginary stuff. That's complex. That's not a real number, right? That's not something that we can write down as a side. And we saw in the very first example we did when we started with law of sines, we got no triangle. That's what's happening here. We're trying to dip into the complex number system to write down a real number, right? And that's got some imaginary stuff to it. So there again, just like in the original example that we did, is no triangle. Which again, we already saw using law of sines first. But it's just a different strategy. But again, I feel, again, this is just personal. I like law of sines to start and then check the ambiguous case. So be on the lookout. It's only in this section where they start introducing these side-side angle triangle cases. But after this section, now everything's fair game. After this section, and even when you take Calc 1, Calc 2, Calc 3, if they give you a situation where it's a side-side angle, it's up to you to be the smart mathematician that goes, that's the one where I need to check for the ambiguous case. The other situations they give you where it's not side-side angle, you attack them appropriately and you get the right triangle. But if you find yourself coming across this situation, it's on you to really have that, that string around your finger that says, oh yeah, that's right. I have to check the second case. It may be there and it may not be there, right? But it's because of the way they present the information, there's ambiguity. So be on the lookout. 7.3 practice, you'll find yourself coming across, number 10 has 2 cases, number 11 has 1 case, number 12 has 2 cases, number 13 there's no triangle. So it's a mixed bag. So again, give it a practice and let me know if you have any questions. Otherwise, we'll stop it there.